This lab deals with resistors, inductors, and capacitors in a series circuit driven by an AC voltage source. The voltage source alternates sine on its terminals in a sinusoidal fashion, causing the current to swap directions. If the frequency is f cycles per second, then the angular frequency in radians per second is 2 pi times f. The voltage as a function of time is just the amplitude, Vs0, times sine omega t plus the phase angle phi, that the source voltage has with respect to the current. In fact, all phases in this lab are given relative to the current in the circuit, which is the same everywhere since the elements are in series. The voltage across a resistor is its amplitude times the sine of omega t, and it is precisely in phase with the current at all times. This is just Ohm's law, that the voltage across a resistor is proportional to the current. The voltage across the inductor is a type of back EMF, because the inductor opposes changes in current. Since the inductor opposes changes in current rather than the current itself, its voltage leads the current by a quarter cycle, or 90 degrees. The voltage across the capacitor is proportional to the charge on the capacitor rather than the current, and thus lags behind the current by a quarter cycle. An oscillating sine function can be represented by taking the y component of a rotating vector with radius given by the maximum amplitude of the function, here I0, and rotating with angular frequency omega. If we take a snapshot and freeze the rotation when the rotating vector representing current is precisely aligned with the horizontal axis with zero angle, we call this a phasor. All other voltage phasors will be oriented relative to this current phasor. The resistor voltage is precisely in phase with current by Ohm's law, and will be drawn as a phasor also aligned with the x-axis, but scaled by V equals IR. The inductor voltage leads the current by 90 degrees, and is thus drawn vertically upward on the Phasor diagram. Since the capacitor voltage lags the current by 90 degrees, its phasor is drawn vertically downward. According to Kirchhoff's loop rule, the voltage from the source is equal to the sum of the voltages across the resistor, inductor, and capacitor. We can't just add the maximum values for these voltages, however, since these are oscillating functions with different phases. The appropriate way to combine these phasor voltages is to add the vectors. The horizontal component of voltage is just VR, and the vertical component is VL minus VC. We then use the Pythagorean theorem to combine the x and y components. Let's now consider the voltage drop across each element. The resistor is easy by Ohm's law, V equals R times I. The capacitor responds differently at different frequencies, with reactance rather than resistance. At low frequencies, the capacitor acts like an open circuit with infinite reactance, but at high frequencies, the capacitor's reactance is reduced, and the capacitor becomes innocuous, like a bare wire with no effect on the circuit. The reactance of a capacitor is inversely proportional to the frequency. In this lab, we don't measure the current directly, so we can judge the effect of the capacitor with frequency by dividing the capacitor voltage by the resistor voltage. This ratio is also expected to be inversely related to the frequency. We can linearize the result by plotting the ratio of Vc over Vr versus the inverse of frequency. The result should be a straight line with slope 1 over RC. Note that this is the inverse of the time constant for this capacitor-resistor combination. At high frequencies, there are rapid changes in the current, and the inductor responds with a large back EMF. Therefore, its reactance increases linearly with frequency, and we expect the voltage drop across the inductor to increase with frequency as well. Unfortunately, the actual inductor used in this circuit has its own internal resistance RL, which must be combined like a right-angle vector with its inductive reactance to give a combination known as impedance, Z. Although the function representing the ratio of VL over VR looks complicated because of the presence of RL, we note that at high frequencies RL becomes irrelevant, and the inductor voltage becomes proportional to the frequency with a slope of L over R. This is the time constant for the inductor. In general, the impedance of the entire circuit, Z, is obtained by combining vectors for resistance, capacitive, and inductive reactance. Ohm's law for this circuit then relates the voltage from the source to the impedance and the current, V equals I times Z. The current is proportional to the voltage drop across the resistor. If we examine the ratio of VR over Vs, we find a function that peaks at a frequency 1 over the square root of LC. This is the so-called resonant frequency of this circuit. It is the frequency at which the current is surging at its maximum. To summarize, at low frequencies, the capacitor dominates the circuit and has the largest voltage drop. At high frequencies, the inductor dominates the circuit and has most of the voltage drop. At the resonant frequency, the inductor and capacitor cancel each other out. The resistor voltage equals the entire source voltage, the impedance is at a minimum, and the current is a maximum. Here is the basic circuit setup. The AC voltage source is applied across the base of the circuit. The voltage sensors to each of the 3 Science Workshop inputs monitor resistor, inductor, and capacitor voltages. It is important to place the red probe on the high voltage side of each element in order to keep the phases correct. Here's how we set it up. First, the AC voltage source. Notice where the red wires are placed. The probe for measuring resistor voltage goes to input A. The probe for measuring inductor voltage goes to input B, and the probe for measuring capacitor voltage goes to input C. The AC source voltage is set to 4 volt amplitude, and the frequency is varied from 10 to 1000 Hertz. At low frequencies, the capacitor has a large reactance, and we expect the voltage drop across the capacitor to dominate the circuit. At only 10 Hertz, note how much larger the blue capacitor voltage is compared with the resistor and inductor. The capacitor voltage is nearly identical to the source voltage. We note the peak values of each circuit element for every frequency. At high frequencies, the inductive reactance is large, and we expect the inductor voltage drop to dominate the circuit. At 1000 Hertz, the green inductor voltage is seen to dwarf the resistor and capacitor voltages and be comparable to the source voltage. A plot of capacitor voltage versus frequency shows the inverse relationship. Plotting capacitor voltage versus the inverse of frequency leads to a linear relationship with a slope given by 1 over RC. The inductor voltage is linear at high frequencies, but varies from linear at low frequencies because of its internal resistance. You can plot the more complex function representing the voltage across the inductor by defining a function and using the actual numerical values for resistances and inductance. The resistor voltage, and thus the current, shows a peak at the resonance frequency. Measure this frequency where the peak occurs and compare with 1 over the square root of LC.